So because I've been asked to a handful of questions about this, I'll go over the Stingray here and in a recording this time, so it's documented. But this is one of the things that I've been working on and off for probably about a year now. And it's one of those long-running projects. Might never actually get finished, you know how those go. But this solves a problem for what happens when you've got a dev kit that you've got to stand up, like this one. And how do you go about doing that? And typically that involves the console cable hanging off of it here, and you might have it set up on a little table, or eventually once you get a couple of them, you might have a workbench or a small closet or possibly a rack shelf that you end up moving these to. But the more of these you have to do, the more they start kind of creating sprawl across the workbench or the area that you have, and it can be helpful to be able to remote into those. Then also with being able to remote into it, that also comes with how can you hook hardware up to CI to be able to get your CI runners working with your hardware and actually testing real physical things as part of your testing process. So that's where Stingray, this little box, comes into play. And it's basically a little remote control for being able to control power on the board, so you can flip it on and off, and hard power cycle and things like that you might need to do physically locally to that board, but when you don't have that local access, as well as being able to get the console out of it as well. And if you're wondering about why console, because don't you have like the Nerves console over over USB gadget mode and things like that? Yes, but not when you're standing up U-boot, and not when the kernel doesn't boot yet, and that kind of stuff, or when you're bringing up a new target platform. So in that case, the only way to really get to the console is through the console header on the board, and so you need some way to be able to get to that. So to take this board, for example, as one of the targets, we got the console cable coming out here. I've got, this one's powered off a USB, so I've got a little USB to Phoenix connector here that just happens to go to this. And I'll just set this board down for a second and grab the Stingray here. And so this has a couple connections on it to be able to wire that up. And so we just go console into USB port and power into the Phoenix connector on here. And this has it's a little customizable, so it'll output 5 volts, so you can run it straight into a USB connector or any board that'll run right off 5 volts, but not every board takes that voltage. Some might be different. So it'll supply 5 volts out of this connector. It's got a little jumper wire to be able to connect it to these inner 2 relay pins. So that's really what's switching the power on and off to the board. And then we got a ground on the other end here. So if you've got a board that takes 12 volts or 3 volts or something that's not 5, just don't power it from this, and just wire straight into the relay, and the relay will make and break that connection to be able to toggle that. So I can show off a little bit of what that does over here. And so this will pop onto the network when you plug it in, just like any other Nerves device through that uses MDNS discovery. So you can get to it with stingray.local. You can also get to it with its full host name. If you have more than one of these on your network, that Stingray name will conflict. So you can use its full identifier here, .local, and that'll pop up as well. Or you can use its IP address. That'll work too. Once you're up and running in here, it gives you a different message of the day so that you know you're in the Stingray device and not your target. This will become important in a second, as you'll see, because when you're booting into a Nerves target or controlling a Nerves target, you're going to get the Nerves message up here. And how do you know which one you're in, especially when you're flipping back and forth on the fly? The other thing, because of that too, the IEX prompt has what I just call the stinger down here of the Stingray. So you get a a little sign down here as well that you're in the Stingray prompt and not in your device's prompt. So if we were to go start controlling this, or actually here, before we control the target board, we've got a target module that we can manage all the targets with that this might connect to. So this version is a single target device. You can only have one connected at once. It's been in my mind for like CI and things like that to be able to have a multi-target device, so be able to build like a rack mount version of this that can control several at a time. So you're going to see everything kind of, this is probably over-optimized at this point, but you're going to see a lot of things set up for multi-target, even though this box that I have right now only controls one. So we've got a bunch of target management here. We can list things that this knows about, so it happens to know that I'm connected over to this this Microchip SAM development kit, and a handful of things that I can do with it. If I want to add a target, there is an add function. All of this has kind of a developer interface right now because it's kind of for developers, so we just went with the easiest approach right now. But when you add a device, basically number, this is just a port number, which this thing only has one port, so basically just make it up on this version. An ID that's a short identifier that's easy to access that device, so I can access this one by SAM, and that's just a pretty quick way to be able to get to this target. A human readable name, so that you have a little bit better description of what's going on with this device. So if you got multiple dev kits or different types, or the AM62 is a great example. There's like 5 different versions of that thing right now, all with different model, different couple-digit model numbers at the end. So this could help you differentiate one from the other. Serial port that's attached to this. So most of the cables show up as TTY USB 0, but if yours happens to show up as something else like AMA 0 or whatever, you're not locked into this only working with like FTDI. It'll work with a handful of other serial connections as well, serial over USB. And then of course the baud rate. So it'll, sorry, I took the default out. So you just put the baud rate in for the board. A lot of them are 115.2, but not all of them are. So if you're working with something else, you can change that too. So now that we know that we've got the SAM dev kit registered in here, the Stingray knows about this target. We can go console into the SAM. So I just use the identifier right there down here. And now it's telling me, okay, I'm in the SAM dev kit. I'm controlling the dev kit. So we've got a handful of commands that we can do with it here. All these commands start with £. Once you're in that Stingray console mode. And this is because when you're typically working with a Nerves device or anything in Elixir, that £, it's used for a couple things, but not too many things. And if you just accidentally type in an IEX, it's not a problem. It just kind of ignores it, or it's a command that you don't have to do the IEX break to get out of. So a little convenience there. So yeah, I just turned it on remotely there, and so now you can see it's powered up. And you just saw it go through the boot sequence, and it's starting up the kernel on this. And this SAM is a little bit slow to boot into Nerves, but you'll see that come up here in a second. So we've got Erlang up, and now we're into Nerves. And so this is the reason why the Stingray looks different. So now that we see Nerves, we know we're in the target board. And down here, we don't have the little Stingray stinger anymore. This is the normal IEX prompt that you're used to seeing. And we could go in here and do a little remote control with it and say, maybe like sys class LEDs. Let's see what's in the blue LED. So like, we'll just turn the trigger off and just turn the blue LED on or something like that. So right now we got the blue LED doing a heartbeat down there. And just to show that this is working, so I just set the trigger to none, LED's off. So we got full control of this board from the Stingray unit right now. So that's kind of nice. If this board were to lock up, or we want to get out, we need to power cycle it or something like that, we can turn the board back off. So I'll hold it up while I do this command. So there's off, board's off again. If we're booted up again, and we see it coming up, one of the other things that can be really nice to do, instead of having to flip it off and on and off and on, is you're trying to change settings or you just want a power cycle, there is a power cycle command. And so that'll flip it off, wait a second, and then flip it back on for you. So all the kind of stuff that you would normally poke around with by hand, having to hold power buttons or flip your power supply and stuff like that, you can get to while you're in the console for that target device. And basically, while you're also in that target device's console, you've got that # meta command there just to be able to access those convenient functions, so you don't even have to leave this console to be doing some of that Stingray functionality. The other nice thing that you might have noticed here is being able to get into U-boot. So as you're standing up hardware and need to be able to get into the bootloader, one thing is, let's power cycle it and get into the bootloader. And it's going to say, hit any key to auto boot. I just missed it. So normally by default, you'll get like a 3-second auto boot from U-boot, and you can press a key there and you'll get into it. So I missed it. We'll do it the old-fashioned way here, and I'll just keep hitting the enter key as it's coming up, and maybe I'll be able to get into U-boot. And there we go. I got the U-boot prompt. So now I can print env, and we've got U-boot environment variables. But what if I'm lazy and don't want to hit enter a bunch of times? Let's just type the U-boot command that launches the U-boot console. And now I'm in the U-boot console. So I see some excitement. I see some looks of confusion of what black magic did I just do here. So this command is just a little macro, just a little helper around rebooting the board and automatically hitting that key to be able to pop into U-boot. And so I could mess around with the environment, the U-boot environment variable, and then I could say, hey, U-boot, go ahead and boot, and now it'll start the kernel, and we'll see it jump back into nerves here. One of the things, if I go back, I can get back to Stingray by #Q or exit. That'll get back to. There's another thing. I'm not going to set it up on this board for the sake of the demo, but I'll show it to you here. Now that you see, you can get into that. If I do target list, there's also a setting here for the U-boot console string. And so this is if your U-boot is password protected. When you get to that U-boot prompt, it will automatically type the U-boot password and get you into the U-boot console as well. So that's one of those things when you're iterating in that U-boot environment, especially in a password protected one. Number one, you could turn off the password for the board, but then that's tedious because you got to recompile and then you got to remember to turn it back on and all that. So this is a way that you can just let the Stingray unit type that to your board each time, and then you don't have to worry about messing around with the password. It's just protected like it should be. And this is configurable per target too. So if you have different hardware targets that you need to work with and they all have different U-boot passwords, you can configure the password per target that you want to access. And, oh yeah, okay. Then there's another fun thing here that's good to know about. So we're working a lot with Nerves firmware as well. And this board, for example, has the SD card in the bottom, and one of the ways that you're going to be getting firmware on and off traditionally is SD card swapping. So you'll pull the SD card, you'll burn your new firmware, put the SD card back in. And especially when you're bringing up U-boot or the kernel, that can get pretty tedious. When you're doing that kind of thing normally in Nerves, once you get to, like when your nerve system is up and you're just doing that with firmware, you've got an IP address and you've got everything in Nerve set up to be able to update here. I'll just show you. So you can do mix target. Let's make that a little bigger for you. So you can do mix target. You go on black mix. I think it's just upload, and then you could put this IP address in here, and it will upload your firmware to that device. But when you're working on U-boot and you're working on the Linux kernel and your board doesn't boot into the kernel or into nerves yet, you can't do this and you're stuck probably SD card swapping, but there's a better way. So let me just go ahead and get, oops. So this is just a little, the demo system I'm running on this Microchip development target here. This is bare bones nerve system. There's a build directory in here, or actually, let me show this off first. So if you do mix target SAM, mix firmware, that's going to build the bundle. Oops. This is going to build the bundle for that, that hardware. It's going to build your nerves firmware. So if you've got, oh, I deleted something the other day. Anyway, I got a file for this. If you go into build, and then you go into your target_dev, and then you go into nerves and images. Well, basically, nerves is where all your fun nerve stuff is. Let me just show this off for a second. So you have your rootfs overlay, which is the root file system and anything that's going to be overlaid on top of it. And then the images directory has this firmware bundle for your nerve system. And so we can take that firmware bundle. So let's copy that to, let's see if I have it in temp. Yeah, okay, I already copied it over there. So let's just go over to temp. So first, let's take a look at that firmware bundle. And if we take a look in here, we've got some metadata, and then we've got this data directory. So we've got boot.bin, uboot.bin, and ubootinv.bin. So there's our bootloader and the environment variables for the bootloader. And we've got the rootfs image that gets unpacked as that root file system. So what we can do is, let's see here, this would be from the Stingray, let's do mix, I might not need to mix target this. So we've got mix Stingray upload. And this is a command where we can put in the Stingray IP. So I'll just copy that over here. We can put in the target ID, which we'll want to upload this for the SAM system, so target number 1, or we can just type SAM. It'll take either of those. And then the firmware path, so local path to the firmware file for this target. So we've got hello SAM here, so let's put that in there and do this. So now it's uploading this firmware bundle for that nerves target to the Stingray, and it's done. So now let's take a look over at, got to remember how to get to this. This is, no, upload manager. Not upload manager, NFS. And let's list the exports. So what this just did is uploaded and unpacked that Nerves firmware bundle onto the Stingray, and the Stingray is now hosting it as an NFS share under its IP address under root share SAM. So now if we go to target U-boot environment variables for SAM, and let's print true. Now I can copy paste this into U-boot. I need to set the target IP address of what the SAM dev kit would be. But now this sets up IP and TFTP on the SAM dev kit in U-boot if I paste this into its U-boot, to where it's going to go out to the SAM and NFS the not the kernel, the other bit. Actually, there's 2 bits. But basically, it's going to NFS all that stuff over, so U-boot's going to network boot from the SAM into the kernel. And then if you do a kernel config, I don't have this part automatic yet, but you can set the kernel config then to boot the rootfs off of NFS instead of the SD card. So you can network boot your entire target platform. So this is something that can help with that SD card swapping so that you don't have to do it and you can run a lot of your stuff over the network instead as you're standing up a system here. Any questions so far? Okay. Yeah, go ahead.
Can this Stingray can be used in the production where you connect bunch of nervous device and then you control them through the Stingray through IP?
So I designed it for development. I guess there's no reason you couldn't use it in production. I just wasn't thinking of it for that. But yeah, I was thinking more of it for like a build farm for CI testing and for being able to do remote stand-up of hardware or being able to do remote management of hardware in like a development environment. Because sometimes when you get to a pile of a certain amount of dev kits, it's hard to have them all running on your workbench or that kind of thing, and you just kind of need it to be remote somewhere, but you still need to get access to it for system maintenance and board stand-up and troubleshooting and things like that. So at least that was the intent. But yeah, really at the end of the day, it's a relay that handles power and a way to do console. So you can really just use your imagination at that point for whatever else you would want to do with it.
That's very cool. And how many devices you can connect to it?
This one is one at a time, but I'd like to be able to build out a version where you can do more. Yeah, this one is slightly beyond prototype right now.
Very cool.
Thank you. Anybody else? I could dive into a little more about how this was built. All right, I'll keep going. So that's the software side. The software is, it is open source right now. I guess I should just point that out. So it is on GitHub. It is on GitHub under my username, McLain, and then Stingray. It's not very documented as far as the README goes right now, but the xdocs are there. So if you run that documentation, read a little bit of source code, but a lot of it's in the module docs to be able to work through how things work and the functions. Like if you're going to a target, that's a bad example here, we'll go to the docs. If you want to control a target, then all that stuff is documented here. So if you look at the xdocs, that's probably the best way to do it right now. I will get to the README at some point, but I got a handful of other things on my plate, so it's probably not going to come quickly. Just to be straightforward with that. And there's a nerve system that goes along with it too. That's just up in another repo on my GitHub that it'll pull down. So a little bit about building this thing. Let me go through here. Yes, thank you for posting the link in the chat there. Let me stop the screen share for a second so that you can actually see probably my screen here better. So this went through a handful of iterations to be able to get to this unit here. I can show off a little bit of that work, but to give you some of the physical design here, the first one, for example, just flat out didn't print right and didn't want to work as I was going through prototyping the enclosure. And so I just had basically bad print. The sides on this were just warped, and just honestly, I don't like this resin. I won't say which one this is. I'll just say I have never had good results with this resin. One of the better prints that came out, the black resin, is one that I've had really good luck with. So prototyping in this, it was almost pretty much dimensionally accurate. There were a couple little flaws in it, but nothing that was a really big deal breaker. So I ran off of this for a bit, test fitting everything together, and then ended up having a went out of house to be able to get a test print done out of house here. And so that was that enclosure. And then once that looked good, went to injection molding this enclosure. So the top and bottom pieces are injection molded. The front and back are still SLA 3D prints. And so that really helps the shell of it be able to scale because you have to order those. I think the minimum quantity was like 50. So that let me order a bunch of those and be able to repurpose them for other projects as well. So for other projects, the front and back panels are swappable to whatever's designed for those for the interfaces, as long as it fits in that general overall enclosure. So a little bit of what that looks like is there's the CAD design for it. And if I go take this apart virtually, so those are the side panels, and it's beagle bone black on the inside. And that's just the Ethernet version there. And a daughter board that sits on top of it. So this is the thing that has the relay and just a little bit of other circuitry to help control the relay and send a higher voltage, send higher current out of these ports than what any one of these I/O pins could provide by itself. And I can show off a little bit of that too. And then just doing a little bit of the mechanical design just to get the standoffs and the spacing and everything right in there with those. And a couple little spacers because it ended up needing those to get to the right height, getting from the SLA print over to the injection mold. Oops, not that. Because the standoffs on each of the prototypes were actually different. So I don't know if it's going to show up on the camera here. I also accidentally broke some of the supports off in one of the torture tests for this, so I know how much stress it can handle. The short answer to that is the SLA prints are relatively brittle, especially the black plastic here, so the injection molded, ABS injection molded parts are a lot more durable. But anyway, if you can see the standoffs in here, they actually rise up about 1/16 of an inch above where the little recess for it goes. On the injection molded design, the standoffs that they were able to provide for that. So I did these are heat staked, and I just did these myself. This whole print was in-house. The ones that the manufacturer for the injection molding provides sit flush here. And with the way that the molding works, you can't and also don't want to space them above that. So I had to do a little something here in the design to be able to work through both types of manufacturing processes. And so on the SLA side, the standoffs just happen to sit a 16th inch above where they would normally be. So on the injection molded side, I just added a little spacer that's 16th of an inch high, and that just sets both those designs to the same height. And then that makes everything line up with the front panel. So if you want to see a little bit about what the injection molding side looks like, this was a pretty cool process. I'm used to working with like mechanical engineers to be able to get this side of things done. So this is one of the things, this is completely a hobby project, by the way. My hobbies tend to look like work. I was interested to go through the injection molding process myself because I've been part of doing it for commercial projects, but I haven't been able to get my hands specifically on the design and into the manufacturer's hands. I've kind of only been able to see what goes out and the results that come back. So going through this process was pretty cool. And what you're able to do, so like I went out to Proto Labs to have this done. And they're really helpful for getting small volume stuff made. So I only had to order 50 of these to be able to get them to accept the order. So that was pretty cool. You're able to upload the design into their system here. And so like the top and bottom of the enclosure here are two separate parts. And that's also important for injection molding. It's a lot more particular when you design for injection molding than when you design for, SLA is somewhat similar. If you can, well, anyway, and then FDM is a completely different process. So if you're designing for injection molding, I think one of the big things I learned is having access to SLA prints can be really helpful. If you can design for the injection mold, it will typically or probably always print on an SLA printer. FDM and SLA, you have to design with different processes. I don't have an FDM printer, so I honestly didn't go that route. I don't have the experience going that side to know what the conversion would be. But designing through this tool and contacting them, they did a design review and all that and gave feedback as just part of the cost to build this, which was pretty cool. Going through that, the advice that they gave me and being able to design this for the injection mold, everything that like these designs came off the SLA printer to prototype this just fine. So that was really cool. But you just go through this and it'll show you things that might be problems with your design. So some of the earlier ones, especially like my first upload here, had all kinds of things wrong with it that it was complaining about. Here it's only got a couple little nitpicks and it's saying like, hey, your edges may be too thin and they might not come out right. And then some of the draft suggestions here. So it's saying like, hey, we're not so sure we can draft this angle in here. We don't know if that's going to come out right. And again, some stuff with the radius. Again, there's like not a problem here because the orange thing that's highlighting is so small. And that's one of the cool things that was helpful about talking to them and going through their human design review as part of this process, is they were able to come in and say, you know what, even though it's showing up here as like flagging this as yellow as it might be a problem, in our experience, you're not going to have a problem with this. This is going to be fine. We see what you're doing. Just go ahead and send it through the system. So they were incredibly helpful with that, and that was really cool. Steel core pins. So it's showing some of these features need metal pins going down into these holes to be able to make this. So they're just saying, here's where we're going to put pins in instead of it being part of the metal mold itself. If I didn't explain that, by the way, injection molding is a metal mold that gets carved out. So like CNC machined out. And then those mold halves get put together and plastic gets injected into that. And then that void space that gets injected with plastic is the thing that ends up becoming your part. So you're dealing with negative space to make the part. You're cutting away from a material versus like the 3D printing type manufacturing that's additive. So you're adding on material to do that type of process. But yeah, then texturing the part. So this does, it has an unfinished texture on the inside because who cares about the inside? And it's got a slight beaded texture on the outside just to give it a little tactile feel and a little bit of grip to it. And we'll just go to the cool part here, the fill analysis. So if you want to see how the plastic's going to flow during the process, it shows it to you there. And so it's showing what the pressure is going to be throughout the part. And so it's filling from this area and then flowing through. I have no idea why it's lower pressure over here than over here, but whatever. It is what it is. It didn't affect the process at all, and I don't know enough about the manufacturing process to know why that is that way, but it's at least kind of cool to see that this shows you how it's going to flow, and you can kind of see one of the things that makes this manufacture okay is it's flowing pretty evenly throughout the part. So if you had your gate somewhere else, actually I'll just get to that here. So here's the gate where the plastic enters the mold. And this is a hot tip gate, so it's just got a tiny little tip there that the plastic's getting injected through. And the trick to this, so anytime you're doing injection molding, you're going to have like a little sprue or a little piece of plastic that's left behind that needs to get trimmed off or sanded down, or if you don't care about the cosmetics, maybe you just leave it. So the hot tip gate is one of the things that was going to leave the least bit of plastic behind. And just to kind of help cover that up a little bit, there's a little 50,000th round recess here. So the tip goes just down into that little dimple. I don't know if you can kind of see it there. Injects the plastic, tip comes off, and then if there's anything left there, I mean, these all came out really nice. They either just sand it down or snip off the remaining plastic. We had talked about other options. So doing what did they call it? Side something gate. I can't quite remember the name. But it would come in here from the side and inject this way, kind of towards the back. This was going to leave a big square tab here, though, to be able to do that. And so they'd be able to cut it off and sand it down a little bit, but because this is a cosmetic face, I didn't really want to have it across there. And this is also a weirder kind of place to put it. So it was pretty cool because they were just able to talk through a couple of the options of the different types of gates that we'd be able to use to build the part, and ended up being able to settle on the hot tip gate here. And cosmetically, I think it worked out pretty nicely. And so when the two halves of that injection mold come apart, that part can get stuck to one side or the other. So there's ejector pins that push the part out of the mold. And those are the things, I don't have an example here. Those are the things, if you look at an injection molded part, you'll see like these little circles on the inside, like on the non-cosmetic side, that get left behind. And those are from these injector pins that are pushing that part out of the mold. So this is a layout for how it's going to push that part out and the pins that they used to do that. And again, the tool with the combination of their application engineers were able to set this up and then tweak the layout a little bit if a person thought there was a little bit better way to optimize this. So I didn't really have to set this out. I just got to see the results of how they were going to set up the pins here, which was pretty cool. The other thing to know about that you have to do in injection molding is none of the surfaces, at least where the mold splits, I'll just put it like this. So there's two halves of the mold, the A side and the B side. And you can see those from the blue half is one half of that mold, one side of that mold, and then the green half touches the other side of the mold. And then they pull apart when the part's done. So nothing in one of those molds that like touches or that's like in one of those cavities can be a straight line that goes down. Otherwise, your part can stick to the inside of the mold. So everything has to have a little bit of a taper or a little bit of a roundedness to it. So that's why these little support structures here have a draft angle to them, have that bevel upwards. And that's also why the case itself is a little bit curved. So, you know, on one hand, yeah, it looks cosmetically nicer that way than a square box, but it's also practical because that helps, that's a little relief to be able to get the part out of the mold. So just a couple little design tricks there to be able to play with that, and you'll kind of see everything has a little bit of a rounded corner on it that doesn't touch the top or the bottom of the mold. So if I were to put the part back like this again this way, this side is flush across the back of one side of the mold, so it can be flat. This is flush against the other side of the mold, so that can be flat. And same with this up here, this surface. But everything else that interacts with that mold needs to have some kind of curve or taper or roundedness to it, so that it can eject out of the mold and not stick or scrape against it. Because either it can get stuck, or if it's scraping against it, it can leave blemishes along the parts that scrape, or along the edges that scrape. So there's a little bit of that process. Any questions over this so far?
Hey, yeah, I'm curious. With the ejection right in the middle, did it have to be right in the middle, or was there an option to put it like right in the maybe in a corner?
Yeah.
Or...
Yep, it totally. Yes, it can be moved around. I happen to go in the middle just so it was symmetrical, especially with the top and bottom of the parts. So it was convenient in this case. But yeah, you could move that. So I think they could, for some reason we couldn't get the hot tip gate in from the other side. Proto Labs has something specific that I don't quite remember with their process, where like they can get the gate on the A side of the mold, but not on the B side, if I remember them correctly. Not all the manufacturers are like that. They just, it's easier for them for the prototyping stuff that they specialize in, so they can use the lower cost machinery for that. Their lower cost, by the way, is still ridiculously expensive. But it's, you know, you're not manufacturing like tens of thousands of these. So that also makes like the draft angle up here. They require like a 3-degree draft angle. They can't do the 1-degree draft angle for pieces of the part that are this big on the machinery that they use for this type of prototyping.
Right, so everything's a compromise. So like
exactly,
the yellow lines that you pointed out would be just fine if you're gonna do 50,000 of them with a bigger manufacturer, maybe.
Yep. And so yeah, like that's where working with their application engineers on the design was great, because yeah, they were able to go through the options of like, well, hey, you could have the gate here, you could have a different type of gate over here. They were able to go and they showed me like, I don't know, 4 different options or something like that we talked through. So yes, if you want to be able to put a gate somewhere else in your design, or you're really sensitive about some edges being cosmetic and the others are not so critical, yeah, like you can move that stuff around, and they'll definitely help with those types of options too.
Awesome, thank you.
Yeah, you're welcome. Any other questions on this, or I can move on to the next step? Cool. Let's go to the other bit then, which we'll go here. So the other thing that had to get made for this was the PCB, because this PCB was custom. So I went to KiCad to do that. And luckily this was pretty simple. So here's the entire schematic for it. So being able to break out the BeagleBone black header, which is pretty simple. It's just 2 46-pin headers. And one of the tricks that I played in this, there's a lot of insertion force when you use 2 headers that are this big and put them into the BeagleBone. It can get really hard to take that back out. So I did the design here with both rows of pins just in the design, but in practice, if I go, I'll show you this in a second, but in practice, I only populated one of these sides of each of the headers. So it was half the number of pins. So it's still not the easiest thing to get the board back out of the socket, but it's significantly easier than if both rows were populated. So that can be a little trick there. If you don't need all the rows of pins and you need the cape part, that daughter board, a little more modular, that's something you can think about. Coming in off the BeagleBone, I tried to keep this project simple, and so we need a few voltage rails to be able to power some stuff, and then we also want, I think I used the sys 5-volt rail to be able to drive 5 volts out to the target board. Then on top of that, we need a GPIO to flip the relay on and off. So a handful of this is just pass-through and relay control, so it's not an overly complicated circuit. I did have a design for this that uses a MOSFET instead of a relay, so this is solid state. There are a couple quirks with that design, and I didn't get the bugs worked out of it by the time I wanted to get the prototype of this out the door, so I did this in good old prototyping fashion and shipped what worked first, and I can go back to the drawing board on the next one. And since these are interchangeable boards, it's not too hard to be able to swap boards out. Yeah, if I want to later, the case can open up just by taking a couple screws out of the bottom. So yeah, GPIO coming in here, a little Darlington transistor to be able to flip the relay on and off. Couple little resistors just so you don't overcurrent that. EMF relay there. So when this is good to know about if you're not familiar with why you put a diode across a relay. That coil is an inductor. It's going to store up energy in a magnetic field when it flips on. And so if that's hooked directly up to your microcontroller pin, when it flips off, when that magnetic field collapses, it sends reverse voltage the other direction. So if you were to drive this either with your 3 volts here or directly off of you probably, actually I could show this in a second. Basically it's going to send that voltage back up your 3-volt rail, in this case, back into that microcontroller's 3-volt power supply, which is tiny-ish on this microcontroller or on this microprocessor. And you don't want it to go there, but you need it to go somewhere when that signal turns off and that field collapses. So if you put the diode in place, then when that field collapses, it can create kind of like a short circuit here and go back through the diode instead of going through your power rail. So if you're designing your own circuit with a relay, that's good to know about. The other thing is, why can't you drive the relay directly off the GPIO? And I forgot to bring the data sheet to the table here, but if I remember this right off the top of my head, the relay takes, I think it was something like 60 to 80 milliamps of current to activate. The GPIO pin is rated for like 6 milliamps of output. So it just doesn't have the juice to be able to drive that relay directly. But if we drive a transistor here, or basically a Darlington, which is 2 transistors, you just get more strength out of it. This is able to let that current pass through. It's able to act like a switch. And so we can drive that 80 milliamps of current with a tiny little 6 milliamp signal. So that's all this is doing. And then this is that Phoenix connector that goes out to that target board there, that little 4-pin connector. So we got a 5-volt rail coming off the, I want to say dev kit, but that's not right in this case because it's not development anymore, off the microprocessor, off the BeagleBone there. So that'll drive that. This is where you can connect that jumper if you want to go to pin 2. If you don't want to use 5 volts, plug whatever power source you want to into pin 2, and that's going to connect into the relay. And then pin 3 goes back out to your board. And if you need to bring it back in, so this might work enough if you're just using an external power supply, just use pins 2 and 3 and break the positive connection and you're good. If you're powering it off of the 5 volts of this board here and you just want it all self-contained, and that works because you're driving it off of USB or something like that, like you saw me show off on this kit, just take the 5-volt rail, do the loop, and you've got a ground connection here on pin 4 to get that return current from the target board back into the Stingray. So pretty simple circuit there. That wasn't too hard to do, and was just able to get that done on a little 2-layer PCB here. So the red is the top layer with the traces and all the components, and the green is the bottom layer, which is basically one giant ground plane. So got some big traces here for that 5-volt rail that powers that target. I can zoom in here so you can see the other stuff. So then here's just the little connections into that relay, that ground that comes back, and a little bit of small traces for just the signal wiring between these components that just flip the relay on. And if you happen to be wondering, wait, why are these this size and these are this size? How did you know to make these? How did you know what width to make these? These are 0.25 millimeters. Normally I design an imperial, but this forces you into metric, so I just had to convert all this. And these are 2 millimeters and so on. How do you pick that? Well, oops. Oh, where did it install to? Stand by. I'll show you the thing that I cheat with. Hopefully. Okay, I won't make you wait. I'll just show you the website. So you can do a lot just between Ohm's law, which is the formula to know for electronics. So voltage over current times resistance. This formula, it will let you pick 2, you can solve for the other. So that'll let you know, if you're using a 5 volts coming in and you need 1 amp going out, then divide, and then that gives you your resistance, or plug in voltage and resistance and you can get current and so on. That solves a lot of how to pick these resistors. For being able to pick things like the trace widths, grab Saturn PCB, which not only has things like Ohm's law in there, but also has things like that, the trace calculator that came up. And so you can plug a whole bunch of those values into this and say, okay, I need this trace here out this 5-volt rail out to my target board. I want that to be able to handle 2 amps or 3 amps. And I want to be able to tolerate a 20 Celsius rise in temperature on that trace as that current is getting carried over that trace. You plug values like that in, and it'll say, okay, use whatever, a 2 millimeter wide trace here, and that'll be okay for 2 amps or 3 amps or whatever you're going for. So then just rate it a little bit more than the current that it's actually supposed to carry. Add a little margin onto that, and that's how I solved for all that.
Yeah,
so
Alex,
yeah.
Out of curiosity, so when you went to manufacture it, though, is it the same thing as with the other manufacturing, where is it maybe cheaper for them to make a 4 millimeter trace as opposed to a 2 millimeter trace? And they have decisions to make there or not? I don't know.
To a certain extent. So if we hop over to not that, this, and then bring you into here. So once you've got that design here done, you can package this up as a set of files and hop over to a site like JLC PCB. Osh Park also does it. PCBWay, I think, is another one. There's a handful of folks that will fab boards now. I actually went this is a Chinese-based company, so it's pretty cheap. Typically the shipping is more than getting the boards over now. But they've got a couple different options. So the big thing will be once you go below a certain trace size. So the manufacturing PCBs, or at least that copper layer on top of it, is a subtractive process. They're removing material, they're removing copper to be able to make it. So you don't get charged for wider traces. You get charged if you need a manufacturing process for tiny traces, which happens if you're using complicated processors or FPGAs or something like that that has really, really small, you're probably dealing with BGAs at that point that have really small ball spacing on that ball grid. So if you need to go small, you'll have to use a better manufacturing process that costs more. Or if you're using heavier weight copper, which really means like thicker copper. So I did all this with 1 ounce copper, which is the standard, and that's also a setting in that calculator as well. If you need to be able to carry more current, you can step up to 2 ounce copper. And these guys also have a setting here for, 1 or 2 ounce. And so if you have to go up to that, then that will cost more as well because now it's more material. And it's probably a little different process.
Awesome. Thank you. It's fascinating.
Yeah, you're welcome. So yeah, that was a little bit of the PCB process here. This is what it looks like when it's when you get it back from their viewer, so you can kind of sanity check what it's going to look like before you hit the buy button on that. If I remember right, these do take about 3 weeks or so to come back. If you're not expediting it, I think they've got options to go faster, but I didn't need this to go faster. So that was pretty cool. And the other thing that goes along with this is, how do you know what each of these components are and what they should be and where you buy them? And that's why you build a BOM. So this is the bill of materials for this project. So it shows like, okay, the capacitor in C1, it's Panasonic capacitor. Here's the properties. We can go to DigiKey, and this is how you buy it. And this is how much you buy it for now. So you can put together a list like this and be able to understand all the parts that are supposed to go into this product. And if some of these get discontinued or you can't get them anymore, or you find something that might be a appropriate, cheaper substitute if you're going that route, especially if you're doing BOM optimization on a commercial project and you're trying to get the cost down, then you can use this list to be able to find substitutes and things like that as well. Actually, here's a good example. These were out of stock. So I had to find a different type of connector and ended up going with this one. So that's how you end up knowing what all goes in each one of these positions here with each one of those designators. So that just corresponds over here. And it'll also give you a cost of the board. So usually these boards cost about 23 bucks to make. Any questions on this? Cool. Well, thanks for listening to me walk through this project. I recorded this one, so this will be up on the Nerves Meetup YouTube channel here in a bit. So you'll have this as a reference.